talk about electric power. Now we've all heard the word power thrown around, but I'm going to tell you exactly what it is. We've already kind of talked about power when we talked about energy. And electrical power is the same as the power we talked about before. It is the energy used or transformed per unit time. So it's the number of joules per second that are transformed. So power is energy transformed divided by the amount of time it takes. In electrical terms, we can define that as the charge times the potential difference divided by the time. Now, if we break this up like this, charge over time tells you the flow of charge past a certain point in a conductor, and that is defined as the current. So it turns out electrical power can be defined by this equation. Power is equal to the current in your circuit multiplied by the potential difference, or the voltage. Now, this is a pretty simple equation, and it should remind you of one we learned about in the last video, which is V equals IR. They're very similar, and they use some of the same elements. Because of that, we can substitute some things. So power is current times voltage, but because V equals IR, we can substitute IR in for V here. So power is also equal to current squared times resistance. So I'm going to keep a little chart over here of all the equations we have for power. We have power equals current times voltage. We now have power equals current squared times resistance. And finally, if we rearrange this equation a little bit, our V equals IR, we know that I equals V over R. So we can substitute V over R in for I, and we end up with power equals V squared over R. All of these are the same thing. We have just substituted. So that if you're given a problem that has current and voltage in it and it's asking for power, you'll use this one. If you're given a problem that has current and resistance and asks for power, you're going to use this one. And finally, if you're given a problem that has voltage and resistance and asks for power, you use the last one. So you have your pick of whichever one of these equations fits what you are given in your problem. The unit of power is still the watt. That is the same, that has not changed, joules per second. Now, let's try and use one of these equations in a problem. So we want to calculate the resistance and the current, so we'll have two answers, of a 7.5 watt nightlight plugged into a US household outlet, which has 120 volts coming out of it. Well, before we do anything else, I want to make a list of what we want to find and what we are given. We need to calculate the resistance, so we don't know that one, and we need to calculate the current, so we don't know that one. But we do know that there are 7.5 watts, and watts are a measurement of power, so we know the power. We also know that there are 120 volts, and volts are a measure of potential. So we know potential, we know power, we're trying to solve for current and resistance. This is where we can go back to our set of three equations here and try and figure out which one will fit. So let's try and solve for resistance first. So we are given V and P, and we want to solve for R. Which one of these has V, P, and R in it? Well, it's the last one. The last one has V, P, and R, and no I. So we're going to use P equals V squared over R. We know the power is 7.5, we know the voltage is 120, and we need to square that. And we divide that by R. A little bit of math here. When you solve for this equation, what you want to do is multiply both sides by R. So then you have 7.5 R is equal to 120 squared. And then you divide both sides by 7.5. And you find that R is equal to 120 squared divided by 7.5, or 1,920. Remember, resistance is measured in ohms, and our unit, our little symbol, is that weird one, omega. So now we know resistance. We know that the resistance is 1,920 ohms. So we've got that part done. But we're not done yet because we still need to solve for the current. So I'm going to erase this. And now we can solve for the current running through this circuit. If my smart board will let me erase. It's moving quite slow. All right. So now we have one of two options. We can use an equation that has P, V, and I, which is how we did it before to find resistance. So we would come over here, and the one equation over here that has P, V, and I is the top one. So we could do power equals current times voltage. 7.5 equals I times 120. I equals 0.0625, and our units are amps. Or, if you wanted to do it another way, you can use Ohm's law. So we know at this point V and R, and we can solve for I. So V equals IR. 120 equals I times 1920. I equals 0.0625 amps. Either way will give you the same answer. It's totally up to you which way you want to solve this problem. If you do both of these and you get different answers, that means something went wrong along the way, and you need to recheck your steps. So that is how you use Ohm's law and our electrical power equation. It turns out that the power companies that come to your house and charge you for electricity use shouldn't really be called the power companies, because you do not pay for power. You pay for energy. They should be called the energy company. So remember, power is energy per unit time. So that means that energy is power times time. And what the electric company does is they come and they figure out the power you consume and multiply it by how long you have consumed it over, the amount of time. Typically, we measure that in joules, right? Energy is measured in joules. But the electric company measures it in something called kilowatt hours. So they take watts, but they measure it in kilowatts because we use a lot of it. And then you multiply it by time, hours. 1 kilowatt hour is 1,000 watts because kilo means 1,000. And 1 hour is 36 seconds. So 1 kilowatt hour is the same as 3.6 times 10 to the 6 joules, or 3,600,000 joules. That's a lot. That's why we measure it in kilowatt hours instead of in joules, because that would just be a pain in the butt. So let's talk about alternating current for a second. The power company charges you for how much alternating current you use, or how much energy you consume in your house. And the energy, the current that comes out of the outlets in your house, is alternating current. So remember, from a few videos ago, direct current flows steadily in one direction. And this is like in a battery. If we have a 1.5 volt battery, we get 1.5 volts of potential difference the whole time, so the current steadily flows. It stays in the same direction, it doesn't fluctuate a whole lot. But the current that we get from a power plant, or whatever we get from the wall outlet, is alternating current. And it changes direction. Goes in one direction, slows down, comes back in the other direction, slows down, changes direction, goes back, and it does this 60 times a second. Now, wires in our homes have very, very low resistance, right? Copper is a good conductor. It does not resist the flow of electricity a whole lot, so there's very little resistance, and the current can just flow through it pretty easily. But if you have too much current flowing through that wire, it can get very, very hot. If it gets hot enough, it can start a fire, which is no bueno. We want to avoid this. So to avoid this, we use fuses or circuit breakers in our houses, and these disconnect the current going through these wires, and they do that by breaking a circuit. So we know that we need a closed circuit in order for current to flow. What fuses and circuit breakers do is they break up that that closed circuit and make it an open circuit, so electricity can no longer flow. Fuses, unfortunately, are one-use items. What happens is there is a little piece of material in here that is sensitive to how much current is flowing through it. And if there is too much current flowing through it, that material will break. Because it breaks, the circuit is no longer closed, and electricity can't flow through it anymore. So you have to go and replace the fuse, which is kind of a pain, but at least your house didn't catch on fire. This is the kind of fuse you find in a car. They work the same way. If it breaks, it has to be replaced. Circuit breakers are much more common now, especially in newer houses. In older houses, you still may have fuses, but in newer houses, most of them have circuit breakers. For example, the dorm that I live in Jacobs, we have circuit breakers. I have one in my apartment. And the way that this works is when there is too much current flowing through it, there's a switch that goes off. When the switch is closed, there is a full circuit and electricity can flow. However, if you get too much current going through it, the switch will open, and then there will be a space within your circuit so that the electricity can't flow anymore. These are really easy to fix. If you have too much current running through a circuit in your house and the circuit breaker is tripped, you just go and you flip the switch and it closes again. Probably want to figure out why it was tripped in the first place to avoid future problems, but it's really easy to reset. The nice thing about this too is if you wanted to do a little handiwork, if you wanted to fix one of your own outlets, you can go to your circuit breaker, flip the switch, and turn off the flow of electricity to that outlet, and that way you don't get zapped. So for homework, I want you to try and answer the following questions, and these have to do with Ohm's law and our new power equation. 1, calculate the resistance and the current of a 1500 watt electric hair dryer plugged into a US household outlet, which is 120 volts. And 2, a 541 watt toaster is connected to a 120 volt household outlet. What is the resistance in ohms of this toaster? So go ahead and answer those and have them ready to turn in the next time you come to class.